Hello everyone. In this video, I'm going to discuss the issue related to transforming a low-pass filter to bandpass filter. You already know the bandpass filter. You have the filter gain, and this is frequency access. So this may be your bandpass filter. So the characteristic of the bandpass filter will end up with higher frequency. Say for example, this is FH, and this is the lower corner frequency, F of L, and you also have a center frequency, and this is so-called F naught. The filter has the filter gain, and the gain will be most likely 1, but at the corner here, you always expect a 3 dB loss, and in the stop band, you also have so-called F of S, and the stop band will be associated with uh, another loss, another gain, right? So was so-called stop band gain. So A or S. The question is, how do we know the order of the filter? In low pass filter, we already learned the formula. For example, if you are designing a Butterworth file, Butterworth filter, you know the formula for Butterworth is n given by half and then log and then some formula, yeah, I cannot remember, but um, it should be 10 and then log 10 and then the frequency, stop band frequency and pass band frequency, or maybe F naught. So here I would say 10 and then A over 10 minus 1, 10 AS, yeah, AP over 10 minus 1. So this is the kind of formula that you can determine the order of the filter to be required to fulfill the specifications. But the question is, you are in a position of designing a bandpass filter. You also need to know the order of the filter. What is the minimum order in order to satisfy the specification? So you may be given the stop band frequency and the stop band gain, but you are not going to be, you may not be given the order of the filter. So what you need is to uh, transform this back to low pass filter, and you just map it. So imagine you have a low pass filter, and this is the gain for the low pass filter, and you need to map this frequency, downscale this frequency until you end up with something like this. The so-called bandpass filter, so-called low pass filter, is actually this one together with an imaginary uh, left side of the pass band. So what you need to do is to use the frequency scaling technique to map this F naught to the center, and you map this Fx to uh, the corner frequency. And obviously you cannot this frequency is non-existent, it's imaginary, but you can still map it. It's a negative frequency. And obviously you can also map, yeah, for example, when you have a stop band gain here, AS. You can map this to here as well. The process of mapping, the process of downscaling the frequency to the low pass filters, to the scale of the low pass filter, require a conversion. The formula for the conversion is here. Omega naught is the uh, center frequency in radian. So you just need to convert this into this one, and replace all the frequency with this, and I will call this F omega palm. So you use this way. So you just replace omega with an omega palm equivalent according to this formula. According to 1. So this is what you need to do. Now, for example, I'm going to transform uh, omega naught. So in this case, I will replace omega here with omega naught. So let's see what we can get. Uh, we will eventually got say omega naught palm, and this is the resonant frequency. And let's say what we can get. And by the way, before doing anything, let's make sure you understand this. Uh, the triangle here represents the uh, fractional bandwidth. Fractional bandwidth is given by f h over f naught, fl, and then divided by f naught. And f naught is the center frequency here, and it is given by this is the so-called f naught. And obviously you can also use radian. to represent frequency. So now going back here, we are trying to find the equivalent in low pass for F naught, and we replace F naught, replace omega with omega naught. So this one become this. Replace omega naught divided by omega, and omega here it become omega naught. So obviously, according to this equation here, you got 1 minus 1, it is 0. So the center frequency of the bandpass filter will eventually be mapped to 1. If you downscale it according to this formula, you get 0. Now let's try FH, the upper corner frequency. So you get this, I will call this palm verse. So we are going to do the same, and then omega H minus omega L, and then omega naught over omega H. So let's check what we are going to get. Omega H square minus omega naught square omega naught omega H. But hang on a minute. According to the formula here, omega naught square is equal to omega L times omega H. So we can rewrite this omega L omega H, and then omega naught omega H. So very clearly, both terms have omega of H, and then we can just take it out, and it will become omega H minus omega L, and at the bottom you got omega naught and omega H, but this omega H is the same as the omega H at the numerator. Then you can just take it out, and omega H minus omega L divided by omega naught is the fractional bandwidth. So you got 1 here. So in other words, when you downscale it, this will become 1. And similarly, you can do the same for omega Fs. This means omega S. Or you can also do omega L. You will eventually end up with minus 1. So omega L palm will become minus 1. And omega S, which it is equivalent to F of S. And let's see what we are going to get. Omega S, omega naught, and then omega naught, omega S. So we cannot simplify it, but we can use this to calculate the new value of the stop band frequency in here in the low pass filter scale. So here it will come omega S. So this is the formula for scaling the frequency. So if you use this formula, then N will become log, and remember A of the pass is minus 3. So it will become 10, and then AS divided by 10 minus 1, and then here it will be purely numerical. 3 by 10 minus 1, And at the bottom here, you can just simply use log. Now remember the frequency scaling after the scaling of the frequency, and we will get uh, omega palm, omega s palm, and then the bottom will be 1. So this will be the formula for determining the order of the bandpass filter. Now, another issue about bandpass filter design is the structure, and you might already know that in, for example, if you have the order, if the order is free, then you will be able to get G1, G2, and G3 from the prototype table. And from here, you can either end up with a full filter topology for low pass, and this one will become L1, L1 will become G1, and this one will become C2, C2 is G2, and similarly L3 will become G3. So you will either end up with this or C1, which is G1, and C2, which is C3, which is G3. So either way, you will end up with a filter for low pass. And this one is high pass, this one is low pass. But how about bandpass? This is the question. And the hints come from the frequency transformation. You are going to use frequency transformation to find a equivalent impedance for the series inductor and the series capacitor, and this is your job. And by doing this, you will end up with a bandpass filter. And I'm going to show you in the next few steps. So first I need to clean up the whiteboard. Just give me a few seconds. Now, suppose you're having a low pass backbone derived from the prototype table. For example, this is the one. So you have L1 here, C2 here, and L3 here. But the question is, you need to, instead of having a low pass filter, you need band pass. You are not using this. So what you can do is, you replace this and find the band pass equivalent. And in terms of admittance, in terms of impedance, this one is going to be J omega, L of 1. And this one is J omega L of 2. And this one here will become a shunt capacitance, yeah? A shunt capacitance. So it will be in terms of impedance, in terms of admittance, shunt subsistence, it will be J omega C2, okay, in terms of subsistence. So I'm going to just bracket it. Just make sure you don't get confused. Now, I'm going to find the use frequency scaling to find the equivalent here. So omega L1 is the reactant here. And by replacing omega with the scale of the frequency, you get J, and then remember what we have done just now. You will get this omega num, and then omega naught, and then omega, and then L1. And I'm not going to call it L1. I'm going to call it Lx, just in case if you are going to apply the same theory for this one, we are going to do that. So we will write the heading here, series component. So we are now dealing with series component. Now, if you do it very carefully, you will get J omega and then L of x. And here you will get J omega log L of x omega. But remember, this one can be further divided. This one can remain unchanged. Omega, and then I'm going to bracket this. And how about here? We'll move the J to the bottom so that it becomes plus. And then omega naught Lx, and then J omega. So obviously, you can replace this as J omega Lx palm. And here you can rewrite this J omega Cx palm, where Lx palm is equals to Lx and then delta omega naught. And Cx palm is going to be omega 1 yeah, I forgot. Yeah, I need to put a delta here. So it become delta and then omega naught and then Lx. So in other words, the transformation you need for the series component is you are going to use Lx and you transform it into and this will become LX pump and CX pump. So this is the component for low pass, and this is the Bandpass. Now we have already tackled the series component, but how about the shunt component? The shunt component has a subsystem J omega C. So we are going to do it as well. Shunt components. And JBX is equal to J omega C X. And according to here, we can, according to what we have learned uh, just now, we can scale this frequency down until it become omega naught, and then Cx. So if you expand this, it will become J omega naught, and then Cx. And here it will become plus, and then omega naught Cx, and then J, and then delta omega. Remember, this is a subsystem. Uh, so very obviously, this one can be grouped, and this one can also be grouped. So what it means here is this one can be split into this one, and we can rewrite it as omega. This one is L Cx pam pam. I use pam pam to represent the shunt component, and here 1 J, and then LX pam pam, where Cx pam pam is equal to Cx omega naught, and L pam pam is equal to delta over omega naught Cx. So in other words, so whenever you come across with a shunt component, such as this one, you can transform it into two shunt components. One is Cx pam pam, the other is Lx pam pam, where Lx pam pam can be found from this equation. Cx pam pam can be found from this equation. So as far as this filter is concerned, you can simply, this is low pass filter, but when you try to convert it into bandpass, all you need is to replace all the series element according to what we have learned here in this table. So for the as far as this example is concerned, then this will become L 1 pound and then C 1 pound. And here C 2 pound and then L 2 pound. And here it will become L 3 pound and then C 1 pound. So this is your Bandpass filter, while the previous one is the low-pass filter. And you can easily calculate the L1, L2, L3 according to the prototype table. And if you don't believe me, you can try try an example. Right? I can try an example for you. So first of all, I need to clean up the whiteboard. Otherwise, I cannot continue. So uh, suppose you are going to design a third order free filter. N is equal to 3. So this is quite simple. Uh, we need to find out the prototype table. And let's assume that uh, let's assume the corner frequency is 2 gigahertz. And the bandwidth is 10%. Let's assume this. So when n is equal to 3, you need to look at the prototype table. According to the prototype table, when n is equal to 3, let's say Butterworth is 1 to 1. So I'm going to use Butterworth. Butterworth topology. So you get G1 equals to 1 G2 equals to 2, G3 equals to 1. So this is your low pass filter. And in low pass, it is, yeah, I also need to have shown the reference impedance is 50 ohm. So you will get L1 is equal to G1, L3 is equal to G2, G3, and C1 equal to 2. So you get this L1, L2, so this is your low pass filter. But obviously, as I said here, you want high pass, band pass filter. So what you need to do is to use the formula that you need, and you replace this with so L1 palm and then C1 palm, and similarly this one and you need C2 palm palm and then L2 palm palm and L3 palm and then C3 palm. So if all the values are properly calculated, then this will be your Bandpass filter. But of course, you need to calculate L1 palm, C palm, C1 palm, all these values. So I'm going to show you how to do it. L1 palm is equal to L1 and then delta omega naught. And remember, you need to multiply it by the reference impedance. The reference impedance is Z naught. Yes, this is what you need to do. So 1 and then 50 and then 10% means 0.1 and then omega naught 2 giga, 2 pi and then 2 giga. So if you do a little bit of calculation, you need to use the calculator. Anyway, I'm not going to calculate this. Let's see if I have a calculator. Yeah, let me do some calculation here. 50 divided by 0. 0.1 and then divided by 2 divided by pi divided by 2 giga. So I got 49 nano. It makes sense. 39 nanohenry. And obviously, L3 will be the same, but we are not going to do anything like this. So I will just say L3 palm will be equal to this. And then we are going to calculate C1. C1 according to the formula is delta divided by omega not Lx, and you also need to denormalize it. So 0.1 and 2 pi 2g, and then the inductor value. The inductor value is 2, is 1, and then the characteristic impedance. And again, I need to use my keyboard. 0.1 divided by 2 divided by pi divided by 2 giga divided by 50. So I got 0.159 Henry. No, pico. So it makes sense. It makes sense. Uh, so this one will be equal to C3 as well. And C2 and L2, C2 pump pump and L2 pump pump. I'm going to calculate this. And according to uh, the formula, it is equal to C2 divided by omega naught. So it will be equal to 2 and then 0.1 and then 2 pi 2 giga. I hope the value will make sense. The capacitance should be large. Again, I need to use my keyboard. 2 divided by 0.1 divided by 2 divided by pi and divided by 2 giga. Let's double check. It looks correct. Wow, super large. And you also need to divide it by the characteristic impedance. Okay, 31 peak. So I missed out here, yeah. I hope you can see the whiteboard. So you need to divide it by 50, which is 50. So uh, so if you do it carefully, according to my calculation, you get um, 31.8 peak. Yeah, sorry, this should be F. And then L2 pump pump. It will be delta and then omega naught and then C2. And this one will be 0.1 and then 2 pi 2 G and C2. C2 is 2. And you also need to multiply by the characteristic impedance. I hope this will make sense. Again, I need to use the keyboard. 0.1 0.1 times 50 divided by 2 and divided by 2 divided by pi and then divided by 2 giga. Wow, quite large one. I hope this makes sense. The inductance is very large. 19 nanohenry. Almost okay, 0.198 nanohenry. It also makes sense. So, in other words, so it all makes sense. So you just substitute this value to the filter here, and this is your bandpass filter derived from the low-pass topology for the low-pass prototype table, and all these values are derived from frequency scaling. Okay, so if you have any questions, please leave your questions to the comment section of this video. Other than that, I think I can close this episode. Thank you. Bye bye.